All right, let's get started. Welcome back, everybody. Appreciate the understanding on Thursday and for moving through the assigned async content. We're rounding out our understanding of higher order functions. And today we'll be looking at, we've been using this for-in operator on sets and dictionaries. We've also seen it with lists, and we're going to dig in a little bit on how it works behind the scenes, which has some implications for these data structures we've been talking about. But before we get into that, we're going to do a little bit of practice. We do have the quiz on Thursday, the last quiz of the semester. I'm almost through setting up the practice problems, and as soon as those are ready, they'll get posted later today. So I'll make a Canvas announcement about that. And you all are sort of used to the format. The quiz will, as close as possible, match the type of questions you're being asked in practice, and you should be well set up for success come Thursday by moving through it. The next exercise is posted, and it's not due until next Monday, but I would encourage, if you're looking for practice, trying to understand these higher order functions, it's well worth moving through. It does cover what we've been doing this unit, and it sort of bridges us into the next. So without further ado, I want to turn it to a warm-up question, and this one I want to stress the intention here is not to diagram. We've learned about these higher order functions, filter, map, and map. And the question that I want you to wrestle with here is these are actually the functions that are built into Python. You don't have to import them. They just exist by default. They exist in the same essence of how we saw their implementations. Like we actually looked at the code that made filter and map work behind the scenes in our implementations. And here we're just explicitly converting the results of filter and map into a list, which I'll explain why we have to do that momentarily. But I want to give you all a chance to think through. The question here is effectively, what are filtered map A and map B after these code listings complete, given what you've seen here? And you can respond on Gradescope for today's submission. Individual responses are great. You don't have to take a picture. It's just a few multiple choice questions to respond to. So let's spend a few minutes on this, and we'll be walking around and can help you if you have questions. Again, you don't need to diagram this. We're just trying to figure out, given the filter and map algorithms, which we've learned, what are the results of this applied to these functions. Is it showing up? Yeah. Okay, cool. two more minutes on this. 2 more minutes. One more minute. Oh. One quick correction to the slide. Sorry about that. The correct type for mapped B is a list of Boolean. So I'll give you 1 more minute given that correction. All right. Let's talk through these and review what we're looking at here. So in this unit, we're looking at higher order functions. One example of a higher order function is a function that takes another function as a parameter. And 2 very classical, famous, and commonly used examples of a higher order function are the filter and map algorithms. In fact, they're so famous, Python has them in the built-in functions that are available to your program without you needing to import them, just like sum and list and other constructors. These are such important foundational ideas that they're there by default. Other programming languages have these same concepts as well. They tend to be built in slightly different ways depending on the programming language, but the same concept applies, where with the filter algorithm, let's focus on that one first. You tend to be given a function as an argument here, and that function is what we call a predicate. It's a special type of function that if we were to specify it in callable form, a predicate would be one where you have some argument, and I'll make it generic of type T, and it returns a bool. All right? So a callable, if we have a list of integers, say here, we would expect T to be int, and so the callable that we would use for our predicate would be something where we give it an int and it returns back to us a bool. Well, B satisfies that callable interface, right? And so that's how we're able to make use of the B function in this particular example. Now, the implications of using filter are, I'm going to imagine sort of this filter step, and let me write it down here. So filter. And the result is going to be, so filter each x, and that's effectively applying the B algorithm, or sorry, the B test, and that's testing whether or not an individual item is evenly divisible by 2. And this is going to be stored in a result of filtered. Right? So the big idea of this algorithm is we move through each item one by one. So we would pass 1 and call the B function with 1. We test, is 1 evenly divisible by 0? That's false. So we wouldn't actually continue adding that to the result of this, right? So if the predicate function, which is B here, if called with an individual item, it returns false, that item does not make its way into the resulting list. We can keep it moving forward and think about, well, what about with 2? So with 2, the filter algorithm would call b with it. 2 divided by 2 has a remainder of 0, so that would be true. This function called a b would return true, and therefore we would continue on and pass that into the resulting filtered list, right? Now we saw the implementation of how you would write this function filter on our own a few lectures ago. And these two are so fundamentally important that we're trying to commit these algorithms to sort of memory and muscle memory so that we don't have to look at the implementations and trace through the loops each time. But I'm going to try and step through it piece by piece here. I'll go 2 more and then pause for questions. So here we, again, try it with 3. 3 is not evenly divisible by 2. That's the function we're calling, so it would get filtered out is one way of thinking about it. 4 would come in, and 4 is, so 4 would make its way to our filtered results. And then I'll pause here before we get to 5 and 6. I'll pause right here. And questions on what we've seen so far? Yep. So even though we haven't defined filtered yet, yeah, I'm kind of taking a high-level approach to thinking about what's going on as the result of this right-hand side. So we're calling filtered, we're building up this list, and we're thinking about how it gets created. And you're right, that it wouldn't necessarily be assigned to filtered quite yet, but we're trying to think through this function call at a pretty high level, so that by the end of this, once we're done, this will be assigned to the filtered variable name. Does that help? Other questions? Yep.
So I'm just going to break this up. So first, you're putting it into the function tree.
Yep.
And then you evaluate if it's true or false.
Yep.
And how are you knowing that you're only supposed to true to the list?
How are we supposed to know to only take in the true value, or to add the values that return true and add it back to that list? So this is the definition of how the filter function, the built-in filter function works. Not on my laptop, I would otherwise pull it up. So we looked at an implementation of this function a few lectures ago. And what I'm trying to posit to you all is that this is such an important concept of a function, of a higher order function, that we're going to memorize that this is the semantics of the filter function, where you give it first a predicate, it's going to return you a Boolean true or false, and then its whole purpose is to move through each item in your input list, so this was x's, call that predicate function with each one, and for each one that it returns true to, add that result to this list. And so in other words, if we want to think of this as a slightly, let me complete this out real quick. So we have 5 here. 5 would not return true in this statement, so that would not get added to our filtered list. And then we would try it finally, the algorithm would move on to 6. And 6 does evaluate to dividing evenly by 2, and so we would add it to this filtered list. The big idea and why this is so powerful is if we gave this function a better name, right? So let's name this isEven. Notice here we could say filter using the isEven function x's. And the way to think about this is, okay, well, we've got this test for determining whether something's an even number or not. And now in one quick little function call, filter isEven is the test that we're filtering by, and then x's. We're able to use this algorithm to select only the values that are even from that input list. And with the built-in filter, we can actually do this with sets, with tuples, and we would see the keys of a dictionary as well. So it's a little bit more flexible than even just requiring a list. It's anything that we'll see as learned, that we'll learn today about an iterable. Well, lists are iterable. And so the big win here is once you understand that this is what filter does, you can very quickly just write a simple little function that's testing one item, and without writing a loop, without writing anything else, call the filter function and apply that test to every item and get a result without having to re-implement that looping strategy. And so here it almost reads It's close to English, right? Filter using the is even function my x's, and the result of that would be only the x's that were even. Other questions on this example? Yeah?
Why do you need the list that goes over the filter?
Thank you for asking this. Why do we need the list that goes over filter? This is a great question, and by the end of today, I think we're going to have a slightly more sophisticated understanding of why. The return type of the built-in filter is actually something that we call an iterable. And it's not a list immediately. It turns out we can take an iterable and turn it into a list very quickly. We could have also turned that iterable into a set, and that would have been fine too, or even a tuple if we wanted. But for flexibility purposes and reasons why I think by the end of today's lecture we'll have a better understanding of the built-in Python filter and map methods, or functions I should say more specifically, those two functions return something that's iterable. And so if we want it to be a list like we're used to working with, we just convert it to a list like that. So it's pretty conventional to turn these things to a list straight away. Or a set if you wanted a set instead. All right. So let's carry this out. So we've got filtered here is 246. That's what would be assigned to that variable. If we wanted to continue this on, we reach our next higher order function call here. And so we're calling the map function. And here we're saying A is the function, the transform function that we're mapping from. And A is this function defined here. It just multiplies whatever its input is by 2. And so ultimately, these results are going to be assigned to the mapped A variable. I'm just going to go ahead and, for illustrative purposes, and write mapped A and start filling in these blanks, right? So very similarly, the map algorithm, unlike filter where we're trying to decide do we keep or reject each item in this input, here we're saying, okay, let's transform each item. So 2 is passed to A. We look at what does A return. A returns 2 multiplied by 2, so this would be 4. That's going to be added. And then map is going to go on to the very next item and say, let's map 4 using the A function. Well, 4 multiplied by 2 is 8. And so that would be the next result. And lastly, we go through and multiply or pass 6 into the A function. This is the map algorithm, and this would be 12. Right? Questions on map. Map winds up being a little bit easier to process than filter because you don't have to remember that step of deciding whether or not something's true and passing it along. Again, the map algorithm is saying given a transform function and some collection or some iterable value, call that function for each item individually and give me the result. Right? And here we again transformed that result into a list. And let's carry on. So the last one here, which I apologize for the typo in the slide. This should have been a list of bool as the return. The map algorithm doesn't require that the input type and the output type of that function, or the parameter type and the return type of that function that it's given, be the same. We can transform between types, and that's what we're going to see here. And there's actually this interesting recognition that a predicate is a special case of a transform, right? A predicate is something that takes any value and returns a true or false value. Well, we can think of that as a transform, and we can use it as a transform as well. So let's try moving through this logic real quick. So here we actually, and notice that our parameter was x's, so we went back to our original x's array, or list. And I should mention that filter and map do not mutate their input lists, right? They produce a new results for you. They don't change the result, or the input that it was given as its collection. So we're going to map. The function that we're mapping is b, and we're storing the results in mapped b. Right? And I'll draw this down here. All right, now this one's kind of interesting. So we pass 1 into b, and we look, what is this return? 1 divided evenly by 2, or what's the remainder of 1 divided by 2? It's 1, 1 equal to 0, that's false. Well, here we're mapping, right? So the map is going to send this a value of false, right? And we continue on in the same idea for 2. So b is mapped to, or we call b with 2. 2 divided by 2, what's the remainder of that? It's 0. 0 equal to 0 is true, so that would map to true here. And we can carry on. And for illustrative purposes, I'm going to move pretty fast here. 3, that's odd, so this would, b would return false. Similarly with 4. And I'm actually going to skip over this middle step. 4 would be true. 5, and then you just change back to blue. 5 would be false, and 6 would be true. One other key difference between filter and map is when you map, you always expect the same number of output results as input results. And here, because we had 6 values, 1 through 6 in x's, when we map b, which is just testing even or odd, we're going to get a resulting list that has 6 items as well. Questions on anything we're seeing here? Yep? Yes. Great observation. So the question is, does filter always return the type that is in the list? So yes, you're always going to get back, if you have a list of ints and you filter that, you're going to get back, int results. So filter is used to try and, like self-described, filter some list based on some test that you want to perform and separate out only the things that return true based on that test. And map is used to call some function and keep track of its results per each item in the input. Other questions on filter or map? All right. So we've been talking about generics and callable types and type aliases, and here's a warm-up question. You don't have to submit this to Gradescope, but 2 minutes on this one, or 3 minutes on this one. What do you fill in the 2 blanks at the bottom with in order for this to be a valid program based on the definitions here? One more minute on this. One more minute. Twenty more seconds. 20 more seconds. All right. Let's talk through this one. So here, last week we introduced the notion of generic types, which in Python require declaring type variables. Effectively, these are type parameters is another way of naming this, but they give us the ability to define types where we can substitute in other types without having to create and redefine whole types or functions based on individual specific types. To be more concrete, it's, for example, with a list, if we can say we have a list of integers and a list of strings, and we're not having, that's a generic type list. We're not having to redefine the notion of a list for each individual type we want to work with a list in. Here we're seeing we can define functions and give ourselves a little bit more flexibility in how we define their parameters and their return types. So specifically, we're declaring a type alias here. And so this is an example of a type alias. And we're aliasing the callable type with a generic parameter type t and a generic return type u, and we're calling this a transform, right? So we're giving the name or the alias transform to this callable type. This is frequently done because we kind of are starting to build a vocabulary. We kind of know what a transform function is intended to do and how it's sort of logically different, predicate is another type of function we can imagine defining generically for use in filter, and they're two different things. So let's look at an example use here. And in this example use in compose, we see that we're defining a function given a transform int float as the first function, or as the first parameter, which is a function type, and another transform float stir. Now here's where you have to connect a few dots and be a little bit careful. So in Python here, because we defined the order of these generic types to be tu, we're going to, in our usage of this, generically down here, we would say, okay, int is going to be t and float is going to be u for that particular function. And for the g function, float will be t and stir will be u. So in other words, what we're specifying with f is f's type is a callable where it takes an int as a parameter and a float is returned, right? So that's what f is. And g is a callable where the input parameter is a float and the return type is a stir, right? And notice we didn't have to, this gives us a way of putting a name on this type of function without having to call these both callable int float, callable float stir, and it allows us to think a little bit at a slightly higher level here. And so we know that we're transforming from int to float, transforming from float to stir, and we put a name to this concept. Yep. What if we wanted more than one parameter? So trying to remember if I have an example of this. I don't believe I do. I thought about doing an example of this. But you could imagine a binary function. And it could be a callable. Apologies, let me move this real quick. And we've got some, we've got some options on what we would do for its parameter types. So we could do t, u, and then we could have a third. Let me make this z for easily determining between u and v. We could have a third type variable if we wanted. If we wanted to say that, no, we want both of those parameter types to be the same, you can substitute t for something that's the same. So stir, and maybe int, we could do it like this. The point is, when you get down to using this binary function, later on, you would say binary func, and then you would just have to say int stir, and you would expect two parameters of type int and a return type of stir, because int would be t and stir would be u. Yeah. So then we would have to have if you have 3 separate types, we would need 3 type variables for that, so TUZ. And then it would be similarly int, float, stir. I'll tell you that we're always going to have, we won't have something this complex. This is the callables we're seeing here with transform is about as complicated as we would go. As you get into more advanced type systems and classes, you can imagine things getting a little bit more complicated, but yeah. So if we now know that f is a callable where we have an int parameter and a float return type, we can look at our 2 candidate functions here and pretty quickly specify b is what we would expect to be called or passed into the f parameter. That's a function that satisfies that callable type. And then similarly, if we look for a function that has a float as a parameter and a stir as a return type, a satisfies that, so we could call it with a, right? And this would type check. Yep. So good question. So the question has to do with how are we substituting these things? And here, notice we're specifying very concretely as these parameters what we want in these individual instances of parameters, what we want these concrete types to be. So you are free at the individual instances to change that up. The question you're asking gets back to what if we wanted, so compose is no longer a generic function, right? Compose, you have to give it an f that satisfies that transform and a g that satisfies the other, right? But if you made compose generic and had its own t's and u's, then they would have to match up in that way. We won't be doing something that complicated either, but yeah. For time purposes, I'm going to skip over tracing this memory diagram. We may come back to this. Or if we don't, we'll put it on the practice, and there will be a solution provided. But we would basically be tracing through the exact same code that we just saw. I want to change gears for just a moment and introduce one more interesting type and give you all a chance to think about this, because this will wind up being very useful as we continue on in the course. Python has another built-in type called a range. And if we think back to our grade school or middle school days of, say, -1, 0, 1, 2, 3, 4, 5, of a number line, what grade do you remember learning like number line type concepts in? What's that? Kindergarten. Okay, so even further back. Schools have gotten better since I was there. So if we're thinking about a range, there are concepts like being inclusive or exclusive of numbers on this range, right? So if we wanted to imagine the range, from 0 inclusive, that's typically illustrated with a closed circle, to say 3 exclusive, you would use an open circle. And if we're thinking about ints, this range would be inclusive of 0, 1, 2, but not 3, right? Similarly, if we wanted the range, inclusive of 4, exclusive of 1, this would be 2, 3, and 4. And hopefully none of this feels particularly mind-blowing, right? In Python, and it's a little bit, you could also imagine illustrating this without a line, because that's a little bit misleading, but instead just circles at the numbers at the integers that are included along the way, right? So in Python, we have the notion of being able to model a range of integers in a very similar way. And this winds up being super handy for producing lists of numbers or writing a simple for-in loop where you don't have to keep track of an I variable in the same way that you do with a while loop and remember to increment it. And I want to talk about how we set this up, and then we'll get a chance to play with it in just a moment. right? So if we think about how do we specify a range, what are the key important pieces of information? Let's say we have some start and some stop. And in Python, the stop of ranges is exclusive, right? Not included in range. And we'll see why this is the convention. So you want to have a guess as to why the stop of a range might be exclusive and why that might be valuable. Oftentimes when you're iterating over a list, because we always start from 0 indices, the length of that list is no longer inclusive, and we'll see an example of that in just a moment. So you would never, if you had 3 items in a list and you wanted to loop 0, 1, 2 for the indices, it'd be nice to specify a range from 0 to 3, but not inclusive of 3, because 3 is the length of that list, and then we would ignore that last value. All right? And so we've got the classical constructor. It looks something like this. So we get a range object by calling the range constructor, and the first argument that we would give it is the start. The second argument is the stop, and we'll talk about another use case of this in just a second. So start and stop. Right? This would give us a range 0, 1, 2. Now, it turns out it's so common that you want to start from 0 that the range constructor says if you only give me one particular value for as an argument, we're going to assume that's actually the stop, and the start will be implicitly 0. Right? So range 3 would be the same here. These are 2 ways of saying the same thing. So the note I would make about this is single arg range specifies type, specifies end or stop. Start is 0. Super handy when we're trying to just have a range of indices and a list, for example, and that's why that's very common. Question from the back, yep. Say that one more time. Can you use this for floats as well? The built-in range operator only works on ints. My belief is as soon as you search for the float range, there is a function that's, you might have to import it. And yeah, we can search for that in a moment. But yeah, you can imagine this being very similarly useful with floats. Yep. Yeah, so we're about to get to the third extra step. There's one more way of calling this, which involves a third argument. So by default, there's this question of how do we increment or potentially decrement each successive value in our range. And by default, that's 1, right? We go 0, 1, 2. Well, what if we wanted 0, 2, 4, 6, 8? There's a third argument that we can give, range 0, and I'll do 5 here for the stop. And then if we give a step of 2, this would give us 0, 2, and 4. And so the third argument is optional. It's the step, and that's over what increment do we want to increase or potentially decrease the next value in this range. All right? So let's try actually making a few examples of this in Python. So if you want to spin up your VS Code real quick, I'm going to switch over to that. I've gone ahead and set up a file named range.py in CL18 directory I added to lecture. Feel free to drop this wherever you'd like. And we'll just set up a few examples using the range operator. All right. So let's try setting up a very simple variable here, such as 1 to, let's say 0 to 9. It's a range type, and it's range 0, 10, right? Now that we have this range object, you'll notice that in Trailhead, if we're looking at what is this, we see that it's just an object that's range 0 to 10. So we haven't done anything with it yet, right? The first thing I want to show you, and I'll do this in the REPL as an example here, is we could say, two numbers, list of int, and it's assigned a list of this range, 0 to 9, right? And if I evaluate that, you'll notice that, so the function I evaluated was I used the list constructor. We're converting some value into, or we're constructing a new list, and its input is this range, 0 to 9. And that ultimately created this variable, two numbers, which is a list from 0 to 9. So really nice usage of a range is you can quickly turn a range into a list or a set if we wanted by using those constructors. Another common usage, though, is, so let's write a for loop here. So iterate using a for in loop. We can iterate using a for in loop by saying for I, say, in 0 to 9, print I. Right? And if I run this example, we see what you would expect. 0 through 9 get printed on each individual line, right? And if I make some notes here, I'm just going to make a note of usages of range. To arg, start, stop, exclusive. 1 arg, and we'll come down and make another example for that. So a 1 arg usage is just the stop, exclusive. 1 is start, or sorry, 0 is start. So we can say 0 to 3 is a range, assigned range 4. And we can try printing the list of 0 to 3 as an example of easily converting to a given list. And then the last example that we had was the 3 arg, where we specify start, stop, step size between items. So let me make this larger. And for that, we can say perhaps odds 1 to 49. Another range starting from 1, going to 50 with a step size of 2. And print list odds 1 to 49. So these are 3 different constructors for shapes of the constructor, and a shape being the arguments that we're passing it. It's always resulting in a range object. that range object is something we can turn into a list, we can turn into a set, we could make it into a tuple if we wanted. And we're going to learn that all these capabilities are thanks to a range being iterable in the same way that a list and a set are iterable. And that's also the reason why we're able to loop over every item in the range. So lines 7 through 9, the for-in loop, are possible thanks to ranges being iterable. And anything that's iterable, we can write a for-in loop over. And each successive run of that particular inner loop, whatever variable we specified as for variable name in whatever our iterable is, in this case it was I, that I will be successively assigned to the next item until we run out of items in what we're iterating over. Right? So that's why it printed 0 through 9, exclusive of 10. Any questions on ranges? Yep.
What happens if your start argument is greater than your stop?
Great question. What happens if your start argument is greater than your stop? So let's try this out. This is actually this is a fun example. So let's add another. So let's try reverse range is range from, let's say, 10 to 1. And we print list of reverse. We've got an empty list, right? Well, this seems like it should be useful, but remember our step is always increasing by 1. So if we added a step of -1, we would actually get the results that you're expecting. Now notice that the stop is still exclusive, right? So if we're stepping by -1, so to have a reversed range, have a negative step, right? But notice we go from 10 to 2 because our stop was 1, and we're always going to be exclusive of that stop. So if we wanted from 10 to 0, we would either have to have -1, oops, not -11, -1, or if we wanted from 10 to 1, we could have had 0, of course. So it's always consistent that your stop is exclusive, your start is inclusive, and we count by whatever our step is. This also works with larger negative steps, so we could do 10, 8, 6, 4, 2, and so on. Right? The last example that I want to give is, so we're used to writing while loops like this, right? And don't copy this while loop down yet. I'm just going to do this really quickly. While I is less than length of some list, let me make this list. X's list, int 1, 2, 3, right? I is less than x length of x's, print I plus equal 1, right? This is bread and butter. Well, it turns out now that we have range and for-in, we've got a more canonical way, or idiomatic way, I should say, of doing this. So this could be replaced with, and this is what I would recommend jotting down. So iterate over each index of a list. We can say, so I'm going to leave this. You do want this x's list here. And we can say this is commonly for I in range of length x's. Print I. And then we could also, actually, let's make this an f string. So we get I, and we also get x's index I. And so this is a really common use of range. And this actually gets to the bottom of why is stop exclusive. Well, it's almost entirely for this particular use case of the range function or the range object, right? So here, we commonly want to loop over every index in a list. So let's make that very common, very simple to do. So we're saying for each I that's in the range where our, this is the 1 usage, length of x's. Well, in this case, that's 3. And that's what's going to cause us to get i's of 0, 1, 2 as each iteration of this loop is executed. And we can very quickly write a for in loop that iterates over each I or index in that list. Questions on this example? So now that you're comfortable with this, or now that you've seen this and can gain some comfort with it, this winds up being a safer way of writing a loop that iterates over every index of a list, right? And the reason for that is you're guaranteed not to have an infinite loop here. With a while loop, if you accidentally forget to increment I, or if you accidentally put that increment of I inside of an if statement that doesn't always run, you run the risk of having an infinite loop that will just keep looping until you actually stop your program, right? This is a little bit safer, a little bit more foolproof, because you're guaranteed for this to stop at the point at which your indices end. Questions on this example? All right. So I want to briefly change gears and talk about this particular statement, right? Actually, let's make one more quick example here, which is in comparison with iterating over a list's items. So the other way of iterating over each item in a list would be for x and x's, print x, right? And I want to point out the key difference between these two ways of iterating through a loop using a for in statement. Notice in the first one that we wrote, we got back an index, I, 0, 1, 2. In the second one that we wrote, we got back each value of each of those items. This might be a little bit clearer if we made these 10, 20, and 30 instead. So it's a little bit more obvious that where we're dealing with items and where we're dealing with indices, right? There are many algorithms that you need to have that index available to you for you to successfully write that algorithm. Like the index is important. And so when you find that you need to work with the index, this range pattern here is your friend. So for I and range of the size of the list. If all you need are the values of the list one by one, you don't have to go to that trouble. You can always iterate through x and x's. But there's something kind of interesting here. That is, how is it that this for in operator actually works? And what can we write a for in loop over? Like, can we say for x in the number 5, print x, right? And we see that no, we can't. And if we look down at it, this isn't giving us the error that I was hoping it would give. We would see, let me try this actually in one other way real quick. So if I try running this directly with Python M, lecture, CL18, range, we see our outputs up to this point like we've seen in Trailhead, and then we see that we get this error. It says the int object is not iterable. Well, what does that mean, right? Because it seems like, what about bool, like a true? And I try running this program again. We see the bool object is not iterable. What about a string, like ABCD? It turns out a string is iterable. And it has to do with its subscription notation. But notice like with a string, if you try and loop over it, its iteration is each character in that string or each successive index. Okay? But the key idea here, I'm going to remove this from my example, is that something must be iterable in order for this for in loop to work, right? And I want to just briefly explore that and introduce you to the idea of an iterator as background to how this works behind the scenes. So I'll have you start a separate file here called iterables.py in the same lecture directory. And we're going to import a special type. So from collections.abc, which is a funny name, import iterable and iterator. And let's set up a reference to a variable named n iterable. Its type will be iterable of int. Okay? And we can assign this, say, we mentioned range is an iterable, so range, and we'll give it, like, say, 5. Right? any iterable value can be used with a for in, right? So for item in an iterable, print item. I'm going to change examples in Trailhead. All right, so nothing new here other than this notion of this type, iterable. And so that's interesting. We're able to assign a range to iterable of specific type int. Could we also assign a set, 10, 20, 30 instead? Sure enough, we could. Could we also assign a tuple, 1, 2, 3? Sure enough, we can. So tuple, sets, ranges, they're all iterable, even though they're different from one another. And so here we're seeing a special kind of type that you'll learn in future classes is called an interface. It's like something that that's common. It's a common interface that's shared between many different types. So iterable types include range, string, tuple. Dictionaries are iterable over their keys, and so on, right? But how does this for in actually work? It seems like there's a lot of magic here. And so behind the scenes, what's going on is we can get something called an iterator out of each iterable. So I'm going to name this next variable an iterator. Its type is iterator, specifically of int. And there's a built-in Python function that allows us to get one of these. So iter of an iterable. I'm going to open up the documentation for this real quick, iter Python. So we'll see this is a built-in, just like others, like input and int, is instance, and there we go, is, or iter is what we're looking for. And we're going to ignore the special case of using a sentinel here and just focus on the single argument case of we give it an object. And basically, what this says is it returns an iterator object, and the object we give it, so the argument object must be something that's iterable. And in this case, we've got a range that's iterable, lists are iterable, sets, and so on, right? So what is this an iterator object? Well, we can kind of see, if I go back over to globals, or go back over to my REPL, we see an iterator is type range iterator. So it's a special kind of iterator. What can we do with this? So there's a special function associated with iterators called next. And we can say next an iterator. And it's 0. But what's special about this is we're actually mutating that iterator so that the next time I call next on it, we get 1. The next time I call next on it, I get 2, and so on. Should not have used 10 as my example, but we're almost there. So range is exclusive of 10, right? So when we ask for the next object or the next value in this iterator, something interesting must happen, right? Well, we do that, and we see we get an error. Stop iteration is the error at that point, right? We can replicate this in code. Let's actually make our range much shorter, so range 3. So stepping through each iteration. So print next an iterator. We're going to copy this 4 times over. But I'm going to comment out this. Actually, let's leave this last one. And we see that we just get the error. And we're going to comment this last one out. It says raises a stop iteration error. So we're digging in a little bit. We're finding out that anything that's iterable, I might actually make a note of this at the top. So examples of iterable types include list, set, range, dict, keys. Great. So we could have assigned anything that's an iterable here as long as each element was of type int, and we can move through it in this way. Now it turns out this feels like it's a step backwards, right? So what we're working towards is understanding how behind the scenes Python is able to actually implement this for-in loop using an iterator on any of these types, right? So how would we make, let's write a while loop that works with any iterator, right? So we're going to once again reestablish this iterator. So an iterator is now again set up to be a brand new iterator for an iterable. Right? And what we've just seen is, okay, we can keep calling this next function until ultimately some error happens. And that error tells us we should stop iteration. So we're going to set up one more variable here that is called hasNext. And this is a convention in many programming languages. We're going to use this convention and just set this up to be true here. So we assume that there's a next value that we could get out of this iterator, right? And we can say while hasNext, so we're going to have this loop that's going to continue running until this hasNext variable becomes false. So eventually it's going to become false. We can have an item. Do I already have that set up? Yeah. So an item is going to be assigned the next of an iterator. And we can print that item. All right, so what we're about to establish is this pattern that we saw for item in an iterable. We're trying to effectively show you how you would do the same thing with using only an iterator object, right? And so we're grabbing the next value, we're printing it. Well, we've got a problem, right? At some point, next is going to cause this error to happen, and our program's going to crash. So we could try this, right? And boom, we get an error. So how do we handle that error? This is a subject that's beyond our concerns, but just for the example today, this is the only time you'll see it. You won't see this on the quiz. You won't see it anywhere else. You'll learn about this in a future class. But to know how to handle an error, we can say, try this given code, except when there's a stop iteration error, and then we're going to say hasNext is false. Right. And we're back in business. Right. So what this code is doing is we're continuing to loop through. No matter how many items are in this iterator, we're going to try to grab the next item, assign it to item, and print that item. As soon as this function says the next of this iterator no longer has any more values, that gives us a stop iteration error. We handle that by saying, do this except when this particular error occurs, and when that error occurs, we're going to cause this line to evaluate, right? Which causes our loop to ultimately end because the next time we jump up to the top, this is false. What I want to say is this is the exact same of for item in an iterable print item, right? And so, wow, how nice of a world is it that we get to live in where we don't have to actually think about how this is going on behind the scenes with all of this, an iterator, trying something, waiting for an error. But under the hood, this is what Python is doing, right? And why do we go to this great trouble to show you this? Well, there's two big takeaways here. The first is, notice that we start from n iterable. And the way that this all works is we need to be able to call, Python behind the scenes needs to be able to grab and get an iterator, which is an object that knows how to move through each item in a collection regardless of the type of collection. So each type of collection has its own type of iterator, right? How you'd move through each item in a set is different than each item in a list. So the big idea here is n iterable, or the item that you're saying for each item in some collection, that must be iterable. So if you want to know whether you can use a for n loop on something in Python, you just search, is this particular type of object an iterable? And if it is, you can write a for n loop with it, right? And then the next big idea is, notice here, each item is, like we obviously see how each next loop, this item is assigned the next value. Well, you have to internalize that and know that that step is happening automatically on your behalf each time this loop enters. You don't see that assignment happening, but you just kind of know by pattern that each time you're inside of this list, each time you're inside of this loop, that item is updated to be the next item. Right? Questions on this before we bring this all home for why this is one other big, awesome thing that we have in our capability here? Yep. Yeah, good question. So why are we doing this 1, 2, 3, and 4 times? So we go back up to the top. Here, we're looping through once, so that's our first loop through. The next time are these 3 that we're printing. And then the next time is this time that we're, what I would call, again, these are the gory details. I'm showing you this, and hopefully it doesn't scar you. You won't have to be worried about this level of detail in the future until you get to a class a little bit later on. But the big point is, this is how it's implemented behind the scenes. There's just this loop is the 4th time we see it printed out. But this loop is always transformed by Python into something that looks like this. And that's really cool because that means anything that gives us an iterator, we're able to use a for n loop on. And you'll learn that you can actually define your own custom data structures and types that you could make your own iterators for, and they would work with a for n loop, which is pretty rad. Other questions on this? All right, so what's the big deal? Or what's one other reason why this is a big deal? So we can imagine implementing an iterable to list conversion function. So we can define a function like toList that is given any iterable type, so iterator of, and I'm going to make this generic, so type var t is type var t, and it produces a list of type t. So all we have to do here is effectively say results are list of t, empty list for item in iterable, results.append item. I've got I need to import type var, sorry. From typing import type var, right? And then return results. And so notice now we have this toList function, and I can say toList and say range 10, and we get back a list object that's 0, 1 through 9. toList, let me try a smaller range here, range 3, 0, 1, 2, toList of, say, a set of, let's do a set notation, 4, 5, 9. And notice we've written a generic function here that can take anything that's iterable. And I apologize, this should have been iterable, not iterator. Anything that's iterable of type t and produce a list of type t. And this is exactly how, this function above is exactly how the constructors list, set, tuple are able to convert other iterables into themselves, right? So here we just wrote what is effectively very similar to the list constructor. And again, we can give it, because ranges are iterable, we can call toList on a range 2 to 5. And we were able to produce our own listing value. You would never yourself need to implement this function. This is how the constructor of a list is doing it behind the scenes and where that flexibility comes from, right? Now, similarly, just to bring this home and to finally come back to the question of why do we have to turn the results of filter and map into a list? Well, in Python, if we were to look at what's the return type of filter or map, it's something that's iterable. And what's really valuable about that is that means you can pass the results of filter or map into a list or a set or anything else, and it's able to produce that data structure for you from the results of listing and mapping, right? Before we close, what I want to stress here is what you're seeing in this example is just beyond the scope of our concerns. This is not going to be on the quiz. This won't be on the final. This is a preview of the types of underlying conventions and patterns that allow us to write these types of programs and how things are implemented under the hood. So if you find this very neat, I would encourage you to continue on in computer science. If you find this overwhelming, I would still encourage you to continue in computer science, but spend some more time with it. We'll be back here on Thursday. I'll post those practice problems tonight. Great work following along today.